Hi and welcome to A4 Rigid Body Mechanics. This is a higher level topic only and I'm delighted to help you get started. We're going to go through this tutorial and help you understand the concepts in this topic. Now I really hope you paid attention in A1 kinematics. In particular, I really hope you paid attention to the equations of motion because we're going to take those equations of motion and apply them to rotational motion in here. I also hope you really paid attention to Newton's first law, Newton's second law, and momentum and impulse in A2, forces of momentum, because we're going to take those concepts and we're going to apply them to angular motion in this topic. So you're already getting to the point where you're taking the standard level material and we're taking that to the next level in this higher level topic. Let's go and start this first higher level topic. Here are the 11 learning objectives that we'll work through. To begin with, it's going to take a little bit of explanation. It's going to take a little bit of you concentrating to get your head around the difference between linear and angular motion. But as we progress and we whiz down this list of learning objectives, you'll find so many similarities that your brain just clicks into action. So without further ado, let's head to the first three learning objectives. The first three learning objectives deal with a concept called torque. To explain what torque is, I want you to imagine a real-life situation. And I want you to imagine you're floating above a door in your house. And I'm going to start with diagram 1 here to explain this. You're floating above the door and down you can see the door hinge and you can see the top of the door. And if you push the door, you can see that it goes round and opens up and lets you into the next room. I'd like you to imagine what happens if you push the door on the hinge. Push it here where this force is shown. Does the door open? No, it doesn't. Okay, so you move a bit further along into diagram 2 and you push the door in the middle of the door. Does the door open? Yeah, it opens. Is it easy to open? Well, there is an easier way, isn't there? There's an easier way where you push the door in diagram 3. You push the door on the doorknob, which is always located at the end of the door. And when you open that door, it opens easily. Similarly, you can open the door by applying a force on the doorknob, but you can apply it just off. It will open, but it doesn't open as easily. What happens in diagrams 2, 3 and 4 is that when you apply a force, it rotates. Now this is different from linear motion, because in linear motion, when you apply a force, it moves. But with angular motion, in this case, when you apply a force, it rotates. And the torque is a measure of how much a force acting on an object causes that object to rotate. And this is your definition of torque. And I'd like you to write that definition down in your notes. But I think as a physicist, we'd quite like a formula for this. And we can kind of guess what the formula includes. Well, we know that the size of force will affect this torque. So it's going to have F in it. We know that the distance of the force from the pivot would make a difference. So it's going to have R in it, which is distance. And also it's going to have something to do with angle, because we kind of thought here that if you push with an angle on that bit, it's going to be harder. So it's going to have theta in it. So we can kind of guess what this force is. And we can also guess even further. We can say, I think the torque would be greater if you make the force bigger. I think the torque would be greater if you make the distance from the pivot bigger. And there's going to be some relationship with theta there as well. Let's not keep you in suspense any longer. The equation for torque is this. Torque is given the symbol tau, and the equation is F(r) sine theta. Well, why is it sine theta? Well, if you look at this diagram here, theta opposite, force, sine theta gives us the perpendicular component of force that acts on the door. And we've seen that maths being used in forces before. So our formula for torque is F(r) sine theta. And torque has units of newtons meters. Sine theta is dimensionless, there's no units for that. So our units for torque is Newton meters. I want to bring you all the way back to linear motion and Newton's laws. And do you remember Newton's first law? Newton's first law for forces in linear motion was the object remains stationary or continues to move with a constant velocity unless acted upon by an external force. And if that was the case, then the object was said to be in translational equilibrium. And what that basically meant was there was no resultant forces acting on the object. Well, the same can be said with angular motion. Newton's first law for angular motion is the object remains stationary or continues to rotate with a constant angular velocity unless acted upon by an external, I don't want to put the word force there. What's the rotational equivalent of force? Torque. Let's have a look at the similarities between Newton's first law for linear motion and for angular motion. Go back to this definition here. The object remains stationary or continues to move with a constant velocity unless acted upon by an external force. Now we go to the angular one. The object remains stationary or continues to rotate with a constant angular velocity unless acted upon by an external torque. The two are exactly the same. As in linear motion, all the sum of the torques is equal to 0, then that object is in rotational equilibrium. And it's kind of important that you write down what the definition of rotational equilibrium is. It's one of those things that might give you 1 or 2 marks in an exam. So in your notes, you're going to write down an object is in rotational equilibrium if there's no resultant torque. And if you want, you can also write down the angular equivalent of Newton's first law. If you remember when we studied Newton's first law back in A2 and we were looking at forces, I gave you some exam hints. And I said if you see the words constant velocity or stationary, then you can tell that that object is in translational equilibrium and you can apply Newton's first law. So the forces to the left equals the forces to the right, the forces up equals forces down. All the sum of the forces is equal to 0. And it's the same when we look at angular motion. There are exam tips and exam hints and keywords that tell you what to do and tell you you're dealing with rotational equilibrium. For example, balanced. I'd like you to consider these two on a seesaw. This small child has a weight downwards, that's his force, and he has a perpendicular distance from the pivot, and we can work out his torque as F(r) sine theta. This small person's torque is working clockwise. And he's going to make this seesaw go all the way around that way, which is clockwise. And I'll show you later why it's useful to think of them as clockwise and anti-clockwise. This girl here has a force acting down the way, that's her weight, and her torque is also F(r) sine theta. But her torque is acting anti-clockwise. That means this person's torque is the same as the other one, but in the opposite direction, F(r) sine theta. If this system is balanced, then this torque equals this torque. So you're looking for the word balance because then you can make up an equation of the anti-clockwise torques equaling the clockwise torques. Another hint you're looking for is the word pivot or pivots. That tells you there's an axis. And if there's an axis, there's rotational motion. So you're looking for the words balanced, pivot. Another word you're looking for is uniform. And let me show you this in more detail. This is a uniform shelf. What that means is the mass is distributed evenly throughout the shelf. And if it's distributed evenly throughout the shelf, that means the centre of mass is in the middle, which means all the mass acts as though it's from that point. So if you see the word uniform, then start to think about, okay, where's the centre of gravity and where's the force acting on this thing that causes a torque? And this here would cause a torque. It would be F(r) sine theta. And that torque, the weight of this shelf, would cause a clockwise torque. Of course, this shelf is in equilibrium because it's not moving. And that means there's another torque causing an anti-clockwise torque that balances it. And you can see that the anti-clockwise torque is the one here provided by tension. That anti-clockwise torque is tau equals F(r) sine theta. F is the tension. R is the distance from the pivot. And sine theta is the sine of this angle here. And because that's providing an anti-clockwise torque, and the system is balanced, then these two torques equal each other. You can set up an equation to work out whatever quantity they want. So your exam tips are, look out for these words: balanced, pivots, uniform, centre of gravity. Those things will tell you that you're dealing with rotational equilibrium and you'll have to calculate some torques. And just to reiterate that, if you see a balanced object, which means it's in rotational equilibrium, then the sum of the torques causing clockwise motion equals the sum of the torques causing anti-clockwise motion. And this makes problems so much easier to solve. Just like there's a similarity between Newton's first law in linear and angular motion, there's a similarity between Newton's second law in linear and angular motion. And do you remember that Newton's second law is based on the fact that an unbalanced force causes acceleration? Do you remember that? And that basically means that when the sum of the forces is not equal to zero, we've got acceleration. The exact same thing happens when we're looking at angular motion. If we have a pulley and we have one person pulling the pulley with 100 newtons and another person pulling the pulley with 50 newtons, and let's say the diameter is 2 meters, this person is providing a torque of 100 times 1, so 100 newton meters, and that's clockwise. This person is providing a torque of 50 times 1, which is 50 newton meters, and that's anti-clockwise. There's an unbalanced torque, and guess what? It causes acceleration. It's exactly the same concept as forces and linear acceleration. Head to your revision note template, write down the formula for torque, the definition for rotational equilibrium, and the conditions necessary for angular acceleration. It'd be helpful for you to draw a diagram to accompany your torque formula, just to remind you about that concept of sine theta. It would also be helpful in the extra notes section to write down the exam hints. And then to make sure you've understood what I've said, complete questions 1 to 5 in knowledge questions. We're now going to look at the concept of angular displacement, angular velocity, and angular acceleration, and I'm going to show you how you can use a set of equations that you already know to deal with angular motion. This slide may be somewhat familiar to you. We used it in A2, and it's to highlight what angular displacement is. The angle in radians, usually, through which a point has been rotated about a specified axis. And actually, for angular motion, we tend to use delta theta, which is a change in theta as a measure of angular displacement. If an object starts here and goes all the way around one rotation, then one complete rotation has an angular displacement of 2 pi. If it does 2 revolutions, it's 4 pi. If it does 3 revolutions, you know what's happening. If it does half a revolution, then your angular displacement is pi. So get used to thinking of that as we progress with these quantities and the formula that we're going to introduce shortly. Angular velocity, again, you've seen that before. Angular velocity is the rate of change of angular displacement with respect to time. Where have we seen that before? Oh, velocity is the rate of change of distance with time. It's the same thing. Angular velocity is given the symbol omega. It has units of radians per second, and we use this angular displacement that we've just talked about as part of that formula. And angular acceleration, we've talked about it a little bit before. We know that an unbalanced torque causes angular acceleration, but we also now have a definition and a formula for it, which is angular acceleration is the rate of change of angular velocity with respect to time. If you paid attention in A2, you'd notice that angular acceleration is getting a little bit complicated. In A2, we were looking at centripetal acceleration, and that was the fact that acceleration was directed towards the centre of circular motion. And we gave it this formula here. And it was measured in meters per second squared. Centripetal acceleration is different from angular acceleration that we've just defined. Angular acceleration looks at the acceleration as it goes round in a circle. How quickly does it accelerate and rotate in that direction? So angular acceleration has a different formula and has different units. It's a different thing. I want to make things even more complicated because there's also something called tangential acceleration. I want you to imagine you're playing snooker and you hit this ball. To begin with, the ball is stationary. Once you hit it, it's going to rotate, which means it will have angular acceleration because it's rotating. But it will also accelerate in this direction. It will have tangential acceleration. But it will also have an acceleration towards the centre, and that will be centripetal acceleration. And if I know IB examiners, they'll love to test you on this. So I'm asking you to keep your eye out for situations where things are rolling without slipping. And by that I mean cylinders rolling down a hill, a ball on a hill, a cylinder, a pulley. Things that are rolling without slipping will have tangential acceleration, and they'll also have angular acceleration. And once that happens, the problems get a little bit more complicated. What can help with these difficult problems is knowing that this expression here joins tangential acceleration and angular acceleration. Now this is not in the data booklet. It's important that you know this formula because this is going to be a lifesaver for you when we get to these 4-mark questions. Earlier I said to you I'm defining all of these things because I'm going to give you a list of equations that you can use with angular motion. Well, here are the equations. I wonder if you recognise them. Let's go with linear motion first. In linear motion we tend to have what I call the SUVAT equations. SUVAT. And if an object is moving with constant acceleration, then you can use this set of equations to work out various quantities of its motion. You can work out the final velocity, how long it takes, and so on. Exactly the same equations exist for angular motion, but we just have to use different terms. We can't call them SUVAT equations because it doesn't spell out SUVAT. It spells out SUVAT. We don't really have a nice name for them, but let's look at the similarities between the two. Our change in position, delta theta, is similar to S. Our initial angular speed, omega I, is similar to U. Our final angular speed, omega F, is similar to V. Our angular acceleration, alpha, is similar to A. And time is the same. We can make up a set of equations that we can use to find out what the angular acceleration is, the change in position is, as long as this motion is experiencing constant angular acceleration. And let's have a look at these equations. For linear, we've got V equals U plus AT. For angular, we've got WF equals WI plus alpha T. It's exactly the same. We're just putting in the angular motion terms. The next one, S equals UT plus a half AT squared. Okay, we've got change in position equals WIT plus a half alpha T squared. What? It's exactly the same. We're just putting in the angular motion terms. And finally, V squared equals U squared plus 2AS gives us omega final squared equals omega initial squared plus 2 alpha change in position. It's exactly the same. If you can get your head around the different terms for angular speed and change in position, then the equations of motion are exactly the same. It's just going to take a little bit of practice. And that's what we're going to do now. Head to your revision note template, write down the equations of motion for rotational motion, and if you feel you need to add anything to your notes about translational acceleration and angular acceleration, add to those on your notes now, and then head to questions 6 to 9 in your knowledge questions. Our sixth learning objective is something called the moment of inertia. And this is where things start to get interesting. Let's think about linear motion and let's have a look at these two diagrams I've drawn here. I've got a truck, number 1, and a person on a skateboard, number 2. Which is going to be easier to push? Well, obviously it's the person on the skateboard. That's because the person on the skateboard has a smaller tendency to resist linear acceleration. Their mass is smaller, right? And it's the same sort of thing with angular motion. It's easier to make some stuff twirl than it is to make other stuff twirl. And that's because of the moment of inertia of something being twirled. The moment of inertia is basically the mass equivalent in angular motion. The moment of inertia of an object is the tendency of a body to resist rotational acceleration, whereas the mass of a body is a tendency of a body to resist linear acceleration. Mass is equivalent to moment of inertia. To find out what the mass of an object is, you basically whack it on some scales, right? But you can't really do that with moment of inertia. You have to use a formula or an expression to calculate what the moment of inertia for an object undergoing angular motion is. And that formula is this. The moment of inertia is equal to the sum of mr² for each body rotating around an axis. And by body, I mean point masses. So for example 1, we have a point mass that's rotating around this axis. So the moment of inertia for this system would be mr². For example 2, we have two masses rotating around this axis. So the moment of inertia for this would be m1r1² plus m2r2². And you can see that that's how you would calculate the moment of inertia for a series of point masses going around an axis. I know what you're thinking. How often do you get spheres going around an axis? That's stupid. Well, you're right, it is stupid. So let me give you some other expressions for moment of inertia. Here are the common objects that experience rotational motion in IB physics. And we've got their accompanying expressions for moment inertia below them. And I want to point out a few things. Quite often in physics problems, you'll have a slope and you'll have either a ball or a cylinder going down that slope. If that's the case, then here we are. We've got the moment of inertia for a solid cylinder and the moment of inertia for a solid sphere. You can derive these expressions. I don't suggest you do. I don't even suggest you memorize them, because in the exam they'll always give you the expression for moment inertia that you need. What I'd like to highlight is that if you look at this solid sphere here, you can see that the moment of inertia is 2/5 mr². You take the same sphere but make it hollow, so have a hollow spherical shell. You can see that the moment of inertia is 2/3 mr². The moment of inertia of a hollow object is greater than the moment of inertia for that solid equivalent. It's the same with a cylinder. If you have the cylinder, you can see that the moment of inertia is 1/2 mr². But if you take a hollow cylinder, then actually the moment of inertia for that is mr², which is twice the amount of the one that is solid. So it's a good exam tip for you to remember that if you have two objects, they both look the same, they both have the same mass and so on, but one is hollow as one solid, then the hollow one will have a greater moment of inertia than the solid one. One of the favourites of an examiner is to ask you to calculate the moment of inertia of a whole system. And to do that, you basically add the moment of inertia of each object. So for example, if we look at this system of objects, we've got two solid spheres, 1 and 2. We've also got a rod that goes around a central axis. To calculate the whole moment of inertia of this system, we take the moment of inertia of the rod, was 1/12 ml². We take the moment of inertia of the solid sphere, which is 2/5 mr². But this sphere does not have the axis there. It's got the axis outside of it, so it actually has an extra element to it. Same with the second sphere. Its moment of inertia is 2 over 5 mr² plus md². And if we wanted to calculate the moment of inertia of the whole system, then we add the moment of inertia of the rod plus 2 times the moment of inertia of that sphere. This is something the examiners like to do. They like you to add up the moment of inertia of different objects in a system. You'll see an example of this when we get to step 2. Right now, what I'd like you to do is write down the general formula for moment of inertia. You might want to note down some of those expressions that I showed you earlier for the sphere and so on. But what you really want to do is complete questions 10 and 11 in knowledge questions. Now we understand what the moment of inertia is and its equivalence to mass, we can take Newton's second law to the next level, and that's what we'll do here. In linear motion, Newton's second law, F equals ma. But in angular motion, we know that the equivalent of a force is torque. We know the equivalent of a mass is moment of inertia. And we know the equivalent of acceleration is alpha. And we can create exactly the same equation. Tau equals I alpha. Torque equals moment of inertia times alpha. It's the same equation. It's just the different terms that are in it. And because it's the same equation, examiners like to make very difficult problems on this. And I have seen in the past 4 marks going to these 2 problems. And let me explain each situation to you. First of all, situation 1. We have a ball rolling down a hill without slipping. It's going to experience angular acceleration and tangential acceleration. Remember we talked about that before. So when we think about that, we're going to write down A equals alpha r. There's formulae we could write up here. The tangential acceleration comes from Newton's second law, F equals ma. But this F is a net force that applies to the ball. And the net force is the force down the hill minus the force up the hill. Well, the force up the hill is F, and the force down the hill is mg sine theta. So the net force causing acceleration is mg sine theta minus F equals ma. That is the formula you want to use for tangential acceleration when you're looking at a ball going down a hill. Equally, you're going to want to look at a formula for angular acceleration. And angular acceleration is tau equals I alpha. Tau is equal to the torque, which is Fr sine theta. So actually what you can come up with is Fr equals I alpha. And you're going to use these 2 equations to do whatever the examiner says. Okay, so they'll ask you lots of things. They might ask you to find the angle of the slope. They might ask you to find the force of friction. But when you're dealing with a ball rolling down a hill, non-slipping, these 2 formulae here will become really important to you. Let's look at the pulley situation, situation number 2. This block here will experience tangential acceleration. It's going to accelerate downwards in a straight line. As a result, this will experience angular acceleration. There's 2 types of acceleration going on here. And we want to make sure we've got some expressions for each of those. Okay, let's go with tangential. Well, F equals ma. That's Newton's second law in linear motion. The force that causes the acceleration downwards is mg minus the tension equals ma. So that's an important equation when we're looking at this type of problem. And for angular, it is tau equals I alpha. Tau in this case would be tension times the distance from the pivot, r equals I alpha. Another equation that's going to be useful for you. So if you see a pulley, you're looking at using these 2 equations. This is for linear and this is for angular. And if you're looking at a ball rolling down a slope, you're looking at these 2 equations. This is for linear and this is for angular. I've put 2 problems in the knowledge questions for you to work through on this. I will also go through questions in step 2, activate the application to make sure you understand how to use these. If you think, what? Forces down a slope? Or what? Forces on a pulley? Then I have 2 extra tutorials in A2. One is called Forces on a Slope and one is called Pulleys. Head back to A2 and you can watch those 2 tutorials if you need more help with the forces involved in slopes and pulleys. In the meantime, head to your revision note template, write down the Newton's second law for rotational dynamics, and head to questions 12 to 16 in knowledge questions. This is where things really just speed up, okay? Because we've seen the similarities. We've seen that the linear equations of motion have an equivalence in angular motion. We've seen that Newton's first law has an equivalence in angular motion. We've seen that Newton's second law has an equivalence in angular motion. And it's the same for angular momentum and torque. Linear momentum is P equals mv. Angular momentum, well, the equivalent of mass in angular momentum is moment of inertia. And the equivalent of velocity in angular momentum is angular speed. So the equation for angular momentum is L, that's the term we give it, equals I omega. Just like in linear momentum, we have a law of conservation. And that law of conservation was, if no external forces apply, then the linear momentum of a system of isolated bodies is conserved. And we did lots of problems on that in A2. The exact same phrase applies for angular momentum. If no external torque acts, then the angular momentum of a system of isolated bodies is conserved. And examiners like to do little problems on that. I will show you that in step 2, activate the application. The similarities don't end. Do you remember that if you change the momentum of something, it was called impulse? An impulse was a measure of the force you applied to an object over time to change that momentum. An impulse was given the notation J. It's exactly the same for angular motion, except angular impulse is given the notation delta L. And the formula for angular impulse is tau, which is the equivalent of force, times time, which is the same. And it's equal to the change in moment of inertia times angular speed. You can see that the 2 equations are equivalent. Just like with impulse, the area under a force time graph was equal to impulse. Well, guess what? The area under a torque time graph is equal to angular impulse. And I think that is where examiners will be examining you. This concept of angular impulse has not appeared in previous specifications. This is a new concept to this new specification. I think examiners will try and extend problems using this concept of angular impulse and the concept of a graph. Head to your revision note template, write down the formulae for angular momentum and angular impulse, draw the torque time graph in your common notes, and go to questions 17 and 18 in your knowledge questions. We're so nearly there. We have one last learning objective. Learning objective 11 is calculate the kinetic energy of rotational motion. I don't even know if I need to go on to the next slide, but let's have a think about it before we do. EK equals a half mv² for linear motion. Let's guess what the equation is for angular motion. EK equals a half. Well, the mass equivalent is I. The velocity equivalent is omega. EK equals half I omega squared. Let's check the next slide to find out. Yay! Okay, it's so easy. One thing I think is important is this exam tip from A3. When I said, whenever you see the term work done, write down work done equals energy transferred. Because I think if you were dealing with an angular motion question and they ask you to determine the work done, I think you'd forget that. And what most problems in angular motion are is finding out the change in kinetic energy of a system. And once you've found out the change in kinetic energy of a system, that is the energy that's transferred, which is equal to work done. So if you ever see the words work done in relation to angular motion, you need to find out the change in kinetic energy of that system using this equation. On that note, head to your revision note template, write down the formula for angular kinetic energy in your revision notes, because now we're going to try and apply all these equivalent formulas into exam style questions. I will see you there.